The Punjab region of northwest India and northeast Pakistan is crossed by 5 great river systems that run out from the Himalayas. They're the Sutlej, the Ravi, the Chenab, the Jhelum and the Indus. And these are feeding sediment out into a basin area adjacent to the mountains. This is the Himalayan foreland basin. In this presentation, we'll be looking at how the tectonics that operate on the margins of the Himalayas interact with surface processes associated with these river systems and their forebears in the geological record. So the foreland basin south of the Himalayas has thick sedimentary successions, and these increase northwards from the Indian Craton in the south up towards the mountain range. Almost all these sediments were deposited by river systems coming out from the Himalayas. They form a succession of rocks known as the Siwaliks, and in outcrop they're represented by sandstones and mud rocks and siltstones deposited in times of flood. We're going to be concerned with the northwest Himalayas up here in the top left-hand corner of the regional map. And on the simplified geological map we can see the region. The yellow areas are areas of active deposition today, and you can see the river systems that run across the region. The area also includes uplifted parts of earlier foredeep sediments shown in the brown, and these abruptly terminate to the north and towards the northeast against a major thrust zone generally referred to as the main boundary thrust. And the main boundary thrust carries rocks derived from the Indian continent that have been thickened up to form the Himalayas. Well, let's start off looking at this area here in northwest India, in the type area for the Siwaliks, in the Siwalik Hills. So here we are looking down on the region on a satellite image from Google Earth. We're looking to the north in towards the Himalayas, which are those snowy peaks in the background. So let's imagine doing a transect from the foreground here in these green colours, which are the foreland basin. We cross a range of hills, the Siwalik Hills, and reach the edge of the high ground of the Himalayas and the main boundary thrust. And the Himalayas then form an orogenic lode that's flexed down the lithosphere of the Indian continent, creating a basin area to the south, which is the foreland basin. But this is not a static situation. The Himalayas are marching south into the Indian continent, and as a consequence are deforming the previously deposited foreland basin rocks. So let's look at a cross-section along that black line. This section runs southwest to northeast into the Himalayas, and it shows that the substrate is inclined northwards under the Himalayas, and the foreland basin rocks wedge out towards the foreland, towards the southwest. Most of these are this Siwalik group package of sediments, and you can see in the cross-section that they're deformed into a series of folds and associated thrusts, and the surface manifestation of these structures are the Siwalik Hills. So the edge of the mountain belt here is represented by spaced thrusts, which deform a thick foredeep sediment and are manifest at the surface by spaced anticlines, the Siwalik Hills. Well, let's go on a tour from here, anti-clockwise, around the Himalayan arc into Pakistan. So we'll be travelling northwards along this satellite image. To keep ourselves located, we can spin around this reservoir, which is almost on the border between Pakistan and India. Mangla Reservoir lies on the junction between two structural domains, the Siwalik Hills we've already looked at, and a place known as the Salt Range, which we're now going to go and visit. So let's spin around. There's Mangla Lake, and there are the two structural domains. Let's spin again. Again, the Salt Range and the Siwaliks, and you can see the Himalayas covered in snow at the back. Zooming down again, a bit closer into the Salt Range, and we'll keep spinning around and around. So there's Mangla Lake in the background. Let's look at the geology nearer to hand. And on the right there, you can see the foreland basin. In the centre, running towards us from the arrow, is an uplifted area called the Salt Range, and another area behind called the Potwar Plateau. And in the background is the main boundary thrust, which separates the inner edge of the Potwar Plateau from the main Himalayan structures. Let's look at a cross-section now along that black line. And it shows that the Potwar Plateau is underlain by a thrust detachment that emerges out into the Salt Range. And to the south-southeast of that is the undeformed foreland basin. This detachment happens on a major salt layer, and it emerges at outcrop here at the thrust front. And here it is. The front of the Salt Range carried on infracambrian salt, with the leftward inclined strata, which postdate the salt, inclined over to the left, represented by the blue material on the cross-section. So that's the Salt Range, and we'll come back to that shortly. But behind the Salt Range is the Potwar Plateau, which is uplifted former foreland basin deposits, slightly older Sewalik rocks, which are now uplifted from the elevation at which they were deposited. Consequently, they're being stripped out by drainage that links down to the Indus Valley. So the previously deposited Sewalik foredeep deposits are being cannibalised, pushed out into the river systems and redeposited in the foreland basin to the south. Let's just step back. And we can see the Indus River running out towards us across the foreland basin. This is a pretty neat image, and we can trace onto it the edge of the Himalayan deformation, in other words, the active thrust front today, which runs around these re-entrants. So the thrust front is emerging into the foreland basin. We've seen already that it uplifts the Potwar to recycle previous foredeep deposits back into the foreland basin system. But that's not the only way in which that thrust front acts. In this area here, which is a place known as the Trans-Indus Ranges, the substrate to the foreland basin is uplifted to create that high range. And if we look into that area there, we can see the effect of creating topography in the foreland basin area. Well, this is a man-made system where a dam has been put across some drainage, and the high sediment load that's carried in these streams has essentially filled up the area that should be a reservoir. And it's not only man-made dams that act to pond sediment in these areas. If we look at the nearer part of the image here, behind those two thrust anticlines, sediment is being ponded today in a large basin area. It's something like 100 kilometres across. So thrust systems, when they first deform the substrate of the foreland basin, can act to create dams to pond sedimentation. But if this deformation continues, these areas can become uplifted and cannibalised and recycled back into the foreland basin. So let's just strip away the graffiti. And let's return over to the Potwar and to the Salt Range. So let's just remind ourselves of the regional section through here, which shows the Potwar Plateau underlain by a thrust detachment that emerges at the Salt Range. The effect of having salt beneath our foreland basin here is to transfer displacement out from the main Himalayan zone way over 100 kilometres out into the foreland basin, which is why the Salt Range is separated from the main part of the Himalayas. Well, let's zoom in on the Salt Range and look at a more detailed cross-section at the front. We can see that the Salt Range itself, on this line of section, is essentially a simple plateau, which is the thrust sheet coming out to the surface. It overrides foreland basin sediments that have been imaged seismically, and the seismic image was also identified a basement step, which has offset the original Salt Range formation and perhaps localised the thrust ramp. But the structure here is pretty simple, although if you notice there's deformation that's beginning to creep out to the south-southeast to create this very low-lying Lila anticline, which is an actively growing structure today. But it hasn't amplified very much yet. So the salt range in this part of the image is rather simple. The width of the salt range itself is defined by the thrust front and the monocline created by the footwall ramp at depth. Okay, so let's leave this central part of the salt range and follow the thrust front along to the east towards the top of this image. And we'll just zoom in onto this area here. And here comes the thrust front in from the west, terminating apparently eastwards. But as the thrust front terminates, the deformation changes style into a series of anticlines, which we can trace in the landscape pretty clearly like this. And wandering its way between the anticlines comes the Jhelum River, coming out of the Himalayas in the north, which is at the top of the image, and running out at the bottom. So the course of the Jhelum River as it merges into the foreland basin is controlled by these anticlines. Let's go and look at it on the ground. And you can see on this photograph where we're looking east, there's the Jhelum River in the background, and you can see on the left of the road a pile of sandstones dipping towards the river, which are deposits of the ancestral Jhelum River, now dipping at 60 degrees, and those strata are only a few thousand years old. So the river is depositing sediment, and then these sediments are being tipped up as the anticlines grow. So let's look at a cross-section through here, through these folds. The structures still detach on the pink salt at depth, but the deformation includes all the foreland basin sediments at top. There's no one single thrust ramp as there was in the main part of the salt range. Let's look at these fold structures. They make some pretty dramatic images in the landscape, looking down on these folded foreland basin sediments. So if we can read the stratal record here, we have a record of foreland basin evolution. So let's see if we can do that. But first, let's have a thought experiment. So here's a very simple view of a lode flexing the lithosphere. And this lode migrates through time. So if we consider a vertical section through some foreland basin strata, what we could do is plot sediment thickness through geological time for a single site. So over time, a particular site will start off far from the lode and get close to the lode. Consequently, the sedimentation rate will increase as the loading approaches, and we should see that by a sediment thickness profile such as is shown on the graph. So the sedimentation record should track the approaching orogenic load. But what happens if the basin floor deforms? We've seen that's happened in the Salt Range and the Transindus ranges. So let's just cartoon on a fold in the floor of the foreland basin. So that folding is generating uplift, but that uplift is competing against the subsidence that reflects the flexural loading of the underlying lithosphere. And what that means then is that this competition will reduce the sedimentation rate at the location. So local uplift will compete against the subsidence. And if this folding continues and outcompetes the subsidence, eventually there will be no sedimentation across this part of the basin. Indeed, those basin sediments could start to be eroded and cannibalized out into the sediment transport system. So let's see how this plays out in the Himalayan foredeep. Well, here's a view onto some pretty spectacular tilted sewalics in the foreland basin. These foredeep sediments were deposited on older substrate there, so they're young from left to right. So that's a sequence in time that we can use to read the subsidence record for part of the floor of our foreland basin. Well, through the late 1970s and early 80s, Gary Johnson and co-workers built up a record of the foredeep strata in this part of Pakistan. And so we're just going to go through one of their locations here. To get a time scale, these workers used magnetostratigraphy, so reversals in the geomagnetic field recorded in the rocks. Well, the obvious representation of the geomagnetic polarity timescale comes from the seafloor spreading and the record of that in the magnetic anomaly patterns that are symmetrical about mid-ocean ridges. The ocean floor basalts record the reversals in the geomagnetic field. And the same is true for sedimentary rocks or lavas, or anything that accumulates in a sequence should show the same record of reversals. And this has been calibrated against absolute geological time. So we have a barcode of normal and reverse magnetic polarity, and the times when the magnetic field reverses have been dated. So we've got an absolute timescale that we can use to calibrate the sedimentation rate in the foreland basin. So here is a measured rock sequence, and rather than show the rocks, it shows the barcode of normal and reverse crons. Each cron, each bar, represents a duration of time when the Earth's magnetic field was in that particular polarity. But because this is in stratigraphic thickness, it also records the amount of sediment that was deposited in that time. So what we need to do is hang this against the geomagnetic timescale. Here we go, with old on the left and young on the right. So over time, the sediment will accumulate, generating a positive slope on the graph. And all we have to do is correlate the barcode in the thickness against the barcode on the global geomagnetic timescale. So let's do that for part of the section. These are the older parts in here, and you can correlate them across like that. Put a line through it, and that gets the sedimentation rate. If we continue up the stratigraphic section, here's some other couple of points up the section. Put a new line through those, and we can see that it's steepened up. So the sedimentation rate has increased through geological time. Finally, the younger part of the section plots over here, and again we can join those up, and we can see that the sedimentation rate has decreased. So let's just interpret it. Let's deal with the older inflection point here, and as sedimentation rate has increased, we can infer that this represents an accelerating subsidence in our foreland basin. In other words, the orogenic load is migrating towards this part of the basin at this time, which is about 9.5 million years ago. But further up this history, we've got a reduction in the sediment accumulation rate, therefore presumably a decelerating subsidence rate. We can infer that the flexural subsidence is now being competed against by the folding of the substrate. So this inflection point here marks the onset of local deformation. So the termination of the record here, where sedimentation has ended, tells us that local uplift has outstripped the flexural subsidence. So in other words, the folding has accelerated faster than the subsidence has been able to. And that erosion is kicking in, and that sediment is being recycled back into the foreland basin. So our thought experiment did pretty well, and is matched by the sedimentation record in this part of the foreland basin. And Johnson and co-workers did the same sort of thing in a number of sites around this part of the foreland basin. So sedimentation is charting two tectonic processes. It's charting the regional flexure due to the loading of the Indian lithosphere by the advancing Himalayan chain, and it's also charting the local tectonic processes of folding and thrusting within the foreland basin. This gives us a tool then for examining the timing of folding in the foreland basin, particularly the initiation of folding. So let's compile some of these results. And in these purple boxes are the duration of folding for various anticlines in the area. We can see that the anticlines initiate at various times and continue growing. In the case of the Mangla Samwan anticline up by Mangla Lake in the north there, the anticline seems to have finished around 1.5 million years ago, whereas the Pavi anticline in the south began folding at about 1.2 and continued folding to 0.4 million years. In fact, that 0.4 is just the youngest age we can get from the magnetostrat in this study. The deformation presumably can continue beyond that and may be active today. Indeed, this area is seismically active. So we can date the age of folding through looking at the stratigraphic record. These folds are amplified together, they have different initiation times, and they amplify at different rates. So it's quite a complicated pattern. And it's through these anticlines that the Jhelum River is wandering. So this has been a presentation looking at tectonic controls. Those tectonic controls include the flexing of the Indian lithosphere to create accommodation for the foreland basin, and this pattern of regional subsidence is modified by local deformation. Collectively, these control the sediment pathways, in other words, the roots of the river systems that flow out from the Himalayas. This local deformation is also responsible for providing recycling back into those river systems, and they also provide local sites of deposition, although we might expect these to be transient. We use the stratigraphic record of the foreland basin sediments to deduce the timing and rates of these local deformations, and to chart the migration of the main Himalayan lodes. So the geology of the foreland basin is charting tectonic processes operating at different scales.